Okay. Okay, everyone can hear me, right?
Yes, doctor.
Okay, so we will start. So today we will do a tutorial exercise concerning the chapter 4 about the turbomachinery and those components in aircraft engine. Okay, in the chapter lectures, okay, in last week, I presented all the components of an aircraft gas turbine engine. Okay, so there are inlet, subsonic, supersonic intakes, and compressor, combustion chamber, turbine, etc. Okay, but for tutorial we will focus more on compressor and turbines. Okay, because there is more important for calculation and for evaluation of performance. Okay. So there are 4 tutorials. We try to do this for today. Okay, so the first one concerning the centrifugal compressor. Okay, centrifugal compressor. So I've added some figures here because I didn't put it in the slides, lecture slides. Okay, so this is a centrifugal compressor. So an inlet of a centrifugal compressor I, the relative Mach number is to be less than 0.97. Okay. Okay, relative Mach number. Okay, so when we say relative Mach number means that it concern. Okay, I've mentioned that for compressor and turbine, we try to consider velocity triangle. Okay, when we want to evaluate the performance, we want to calculate the velocity of the compressor and turbine. We try to characterize them in terms of a velocity triangle. Okay, velocity triangle. So the velocity triangles has the components absolute velocity, rotational speed, rotational velocity, and the relative velocity. Okay, I think you understand this since you have learned in mechanical. Okay, in solid mechanic or something like that. Okay, mechanical. So you have normally for a material or anything or even fluid, we have absolute velocity, means the actual velocity within for us is the fluid, which is the air inside the engine. So absolute velocity is the velocity of the fluid, air at that time. And then we have rotational speed, rotational velocity. So that rotational velocity is the velocity of the blades, okay, blade of the compressor and turbine. And so absolute plus rotational. So we have relative. Relative velocity is the one that we measure and we see, okay, that we measure. So actually the one that we measure is actually the relative velocity of the fluid, which is depends on the rotational speed of the blade. Okay, so I'm going to, before we start the tutorial, I'm going to sketch a bit the velocity triangle so that hope you understand. Okay, so for centrifugal compressor, so means center. So imagine we have, okay, axis like this. So this is axial axis. We have radial, and this one is the tangent. Okay. So for centrifugal compressor, we imagine that okay, normally the fluid will enter axially, means on this axis. Okay, so if we have the triangle, it will be like this. Okay, so this is this plane, axial and tangential, will be the plane for the inlet of the fluid, inlet at the compressor. This plane, radial and tangential, will be the plane for outlet. Okay, so we have something like this. Okay. So this is, we name it C1. C1 is the absolute velocity of the fluid entering the compressor. Okay, so U1 will be the rotational speed of the blade of the compressor, and so absolute and rotational. So we have relative velocity that we know it as W or sometimes V. So here we use W. So this is the relative velocity. So you imagine the fluid entering the compressor axially in this direction, the absolute velocity, and then it will come out in the radial tangential plane like this. The fluid outlet coming out from the centrifugal compressor will be in this plane. So we have W, okay, and U, rotational, and this is the absolute velocity, like this. Okay, so if you remember in the slide, in the lecture slide, I'm searching for the page. Okay, this one. This one. Okay, this slide, right? Okay, so okay, this is the how the fluid flow inside the centrifugal compressor. So this is the side view, the tepi side view. This is the side view. This is from the front view. So the air enter the fluid enter the centrifugal compressor. Imagine this is the axial axis. Okay, this axial line. So the fluid will enter this way, horizontally like that. If you view it from this side, okay. So the fluid will enter this way, okay, and it will come out from this side view this way. It will come out this way. So that's why radially this plane. Okay, so if we look at from the front view, okay, this is the front view. So the fluid enter, the air enter at this center, okay, this center, and it will come out radially. That's why the axis is named radial. Depends on the radius, the line of the radius of the blade. Okay, so radially, okay, like this. Radially will come out this way. Enter at the center, and it will come out this way. Okay, like this. Okay, from the front view. Okay, so for at each of the between each of the blades, okay, the air will come out this way. So that is radially. So okay, so we have to understand first how the fluid enter and come out from the centrifugal compressor, because we are going to sketch the velocity triangle, so we have to know the direction. Okay, so back to the exercise. Okay, so the relative Mach number is to be less than 0.97. So we try to achieve a 0.97 relative Mach number. So when we say relative Mach number, means it concerns the relative velocity. Okay, to eliminate the formation of shock waves and its attendant loss. Okay, the root to tip radius ratio is 0.4. Okay, I'm not sure if you can view this one. Okay. This I just put this graphic figures for you to understand better. Where is those parameter, the values? Okay, so this is the root to tip radius ratio is 0.4 at the inducer. Okay. Okay, at the inducer is zero. Okay, the blue one, this one is the compressor. This one is turbine. So we forget first about the turbine. We just focus on the compressor first. Okay, so this is the inducer. Okay, this is the inducer. Okay, fresh air flow in axially this way, and the outer side is the exducer. Call it exducer. So we focus on the inducer. So when we set the root to tip radius ratio, root at the center to tip at the tip of the inducer. Okay, so the whole of this is the inducer, root is the center, and the tip is at the outline of the inducer. Okay, so the radius of the root to tip is 0.4. Okay, the ratio, not the radius, the ratio is 0.4. Okay. Dia nak masuk. Okay, then the inlet velocity is axial. Okay, so it's correct, it's axially. So they enter, the fresh air enters axially. Okay, sometimes why we have to mention this, because sometimes the fresh air, the fluid, sometimes it has pre-wheel, means that it has an angle a bit, that we characterize it as alpha. The angle means that it doesn't enter the compressor axially direct like that. Sometimes it has a bit angle that we call pre-wheel angle. But for these questions, exercise 1, the inlet velocity is totally axial. Okay, so there is no alpha or any angle, and uniform over the impeller eye. Okay, impeller is something like this. Okay, impeller eye. Okay, just put the you can Google it also, but I just put the figure so that you understand. This is like the we call this, okay, this one, or this is the impeller. So the eye is at the center. Okay, the eye tip diameter is 20 centimeter. Okay, so eye tips diameter. So diameter eye tip is about it's like the this do a bit. Okay, the eye tip diameter, whole of this. Okay, this is actually the inducer disc. This is 20 centimeter. Okay. Okay, it's correct. Okay. Okay, eye tip diameter means that the whole of this eye inducer is diameter is 20 centimeter. So we know just now the ratio, and this time this one is the diameter. Okay, determine the maximum angle mass flow rate throughout for a given rotational speed of 486 rotational per second. Okay, so maximum angle mass flow rate is the beta. Okay, that's why we have to draw the velocity triangle, so we know where beta and where is alpha situate. In this question, there is alpha is 0. Okay, but we have a value of beta. Beta is the value of the relative velocity, the angle between the relative velocity and the rotational speed u. Okay, throughout for given rotational speed. So rotational speed u is 486. Okay, we are given that. Okay, so let's start. Okay, let's start. So understand. Okay. I will do we need, okay. The mass flow rate, okay, I'll give mass flow rate equation, okay, formula. Okay, the mass flow rate at the inlet, okay, the mass flow rate of the, normally we calculate it at the inlet because it's more easier. Okay, the mass flow rate of the fluid entering the compressor will be m, okay, rho 1, if we calculate at the inlet, rho 1, and then c, okay, the velocity, the absolute velocity. So we need axial, CA is the axial component of the absolute velocity. Okay, so C, the absolute velocity, has the component CA, which is axial, and CU, which is tangential. Tangential like this, axial like this. Okay, so to calculate the mass flow rate, you only need the value of the axial, because okay, okay, because okay, if you look at this this slide, this slide better. Okay, okay, because you look at this. Okay, so the direction of the fluid entering the compressor is in this axial. Okay, so that's why we only need the component, the axial component of absolute velocity, CA. Okay, we don't need the tangential. Okay, and CA1, rho CA1, and of course the area, inlet area. Okay, times inlet area. So the inlet area, okay, at the inlet, the area at the inlet will be the whole pi d, okay, the whole area, the circle, okay, pi d square over 4, okay. Later on we see the calculation. So continue this one.
Doctor, someone is in the waiting list.
Okay. Okay lah. Okay, so okay, now we calculate. Okay, how do we start? We start by, okay, we have the rotational speed in rotation per second. So we change that into meter per second. So U1 pi d, okay, d of the I tip, okay, and n, okay, the rotational speed. So we change this into meter per second. Pi diameter is 20 centimeter. We take the I tip diameter, and n is 486. Okay, so we get we have around 305.36 meter per second. Okay, so that is our rotational speed in terms of meter per second. Okay, next, to calculate maximum angle, okay, maximum angle mass flow rate. So ada lagi. So we need to calculate first the value of the velocity, okay. So we use m because we have the m relative, okay, Mach number. So when we say relative means that it relates with relative velocity. So we need to use the relative velocity W1 over gamma RT, gamma RT. Okay, square root gamma RT, the Mach number. So W1 from the velocity triangle, we know that W1 is C1 square plus U1 square root. Okay, Pythagoras, okay, square root of C1 square plus U1 square from the velocity triangle. And gamma RT1, we need to change it because we have the value of the temperature. Mesti tak bagi temperature. Oh, it's okay. The temperature is the like the ambient 28. We take 288 Kelvin. 288 Kelvin. Okay, and 101 bar, 101.3 kilopascal. Okay, the total and pressure total. Okay, so this one T temperature is the static temperature. So we need to use the total temperature. So we change the relation between static and total. Okay. So gamma R. Okay, so this one will be T total 1 minus the absolute velocity to Cp. Okay. Okay, remember this one is like static plus dynamic, okay, values, static plus dynamic. So this total minus the dynamic temperature. Dynamic temperature is like the the kinetic, okay, kinetic like kinetic energy. Okay, C1 square absolute velocity over 2Cp, okay. This one is from total static dynamic relation. We change it T1 to T total minus the dynamic temperature. Okay, so we know U1. Okay, U1 from here 305.36 meter per second. R and gamma is the parameter, so we take R R287, we use R287, and gamma 1.33, we can take 1.33 or 1.4. Okay, so we only, and this one is 0.97 given. So we only have, we only left with C1, absolute velocity, unknown. Okay, all of this, the other part is known. We can calculate it. Okay, so we only have C1. So we rearrange this equation to calculate C1. C1, okay. After we get C1, then we have to calculate the pressure, the static pressure, density, etc. And then we achieve to mass flow rate. Because remember just now the equation for mass flow rate, rho 1, C, and area. So that's why we need to calculate density, etc. Okay. So C1 first, C1. So rearrange from this equation, we get C1. Okay, so C1, okay, I already calculated, I give you the answer, later on you check, 114.62 meter per second. 114.62 meter per second, okay? Okay, from this equation, this one is 0.97, this one you want 305, gamma use 1.33, R287, T total 1 is 288 Kelvin, C1 unknown, 2 CP, CP 1005, okay, joule per kilogram per Kelvin. Okay, okay, so you get C1, 114, and after that, okay, from C1, okay, then we have to calculate T1. Okay? Because we want to use the ideal gas, we assume this is ideal gas. We want to use the ideal gas relation. Remember the P rho RT, rho equals to P over RT, the ideal gas equation. So that's why once you get the absolute velocity, we use the absolute velocity to get the static, because the ideal gas equation need to use static value. We can't use total value. Okay, so once you get C1 absolute velocity, we use back this total static total dynamic relation to get the static temperature T1. So T1 is 281.5, something like that. T1 281.5 Kelvin from this relation. Okay, once we have known C1, we get T1. And okay, the ideal gas equation relation. Okay, ideal gas relation. Okay, so we use this one to, if we want to calculate, next is pressure. So we use this one, PO1 over P1 equals to TO1 total P1 gamma minus 1, okay? The ideal gas equation. So we have P total 288, P1 is 281, P total 1 is given just now, 1 bar, around 101.3 kilopascal. So we can calculate P1, the static pressure. Okay, so static pressure 93.5 for kilopascal. You can leave it in kilopascal, it's okay. Okay, because we have the total pressure just now 101 kilopascal, so we can leave it in just kilopascal, 93.48 kilopascal static pressure at the inlet. Okay, so we can calculate the density. So you can't just use density, the normal value density of air, what? Okay, you have to calculate it. Okay, even though the value will be around 1 kilogram per meter cube, but you need to calculate it also. Okay, so so rho 1, you use the ideal gas equation, P1 over RT1, the ideal gas equation. That's why just now we need to calculate pressure and temperature. Okay, so the ideal gas equation, we get 11157 kilogram cube. Okay, Row 1. So what else? Just now the mass flow rate. We have density, we have velocity, and last one we need is the area. Okay, the inlet area. Okay, so the inlet area, obviously we have to use the information on the ratio, diameter, etc. Okay, area. Okay, so area A1 pi over 4. Okay, the normal equation area for a circle. Okay, so we use diameter DE. Okay, diameter at the tip, at the eye tip square minus the diameter at the root. Okay, because this one kan. Okay, see this side view, eye tip diameter. So eye tip diameter minus the diameter at the root, because the fluid only flow between this. Okay, so you have to take out, okay, minus the diameter at the root. Okay, so diameter tip square minus diameter at the root square. Okay, because the fresh air, the fluid only flows here. Okay, so minus the root. So the area. Okay, so the area, the eye tip area, we have the eye tip diameter. Just now we have 20 centimeters, so 0.2 meter. And for the root, okay, we have the ratio. The root to tip radius ratio is 0.4, so we use that ratio. Okay. So that ratio is the ratio between the root, okay, this one, the diameter root to the tip. Okay, so this one you can factorize this one, okay, because this is, you can use the ratio. So you have A, the area 0.0264. 0.0264 meter square. Okay, 0.026. So the area is actually quite small. Okay, around 0.0 something, or 0 point something like that. Eh? Okay, 0.0264 meter square. Okay, so once you have all these values, so you just combine all of that to get the mass flow rate. So mass flow rate just now, density times C1. So since the fluid enters totally axial, okay, only axial direction, there's no tangential direction. So means that the C1 that you get just now is actually equals to CA1, the axial component of absolute velocity. Okay, not just that we have triangle, velocity triangle, relative plus absolute, get rotational, etc. This absolute velocity itself is has two components, which is CA, the axial, and CU, the tangent. Here, for the centrifugal compressor, this exercise one, there is no tangent component because the velocity enters totally axial. So you means that C1 that we have is totally equals to CA1. Okay, so you can calculate directly M mass flow rate rho 1 CA1 and the inlet A1. Okay, so we get 3.5 kilogram per second. So only quite small. Okay, 3.5 kilogram per second. Okay, so that is the mass flow rate. Okay, the mass flow rate 3.5 kilogram per second. Okay, then just a bit calculate the beta. because the angle, for the angle. So beta, so if we understand the velocity triangle just now, okay, you have the velocity triangle like this. So C1, U1, W1, okay? So beta is this one. Okay, beta. Okay, beta 1. So, okay. So beta, okay, so this is beta. So we use the tangent. Tangent beta 1. Tangent beta 1 is C1 over U1. Okay, tangent beta 1 is C1 over U1. So we get beta 20.57 degree. Okay? So this is the velocity triangle of the centrifugal compressor. So tangent beta C1 over U1. So you have 20.57. Okay, so that's it for the first exercise. Okay? Okay, so everyone, any question? Angkat tangan nanti. Izzati? Tak ada.
Tekan.
Okay. Okay. So we proceed with second one. Don't be shy. Okay, second one. Second one is the axial compressor. Okay. Apa nak melukis? Yeah, I need to explain first the velocity triangle before we start the exercise. Okay, so for axial compressor, axial compressor, we use this, this triangle. Okay, CAU, okay. So this is C1, the absolute velocity, and then we have W1, the relative velocity, and rotational speed U1 in this direction U1. Okay, so imagine this is like the side view of an axial compressor. Do I have the photo? Axial compressor. Tak sangat. One stage. This one. Okay, this is example of axial compressor like this. So it has several stage. Okay, so this is from the side view. So the air enter axially in this direction. So and the blade will rotate in this way. Okay, rotate this way, axial like this, horizontally, and rotational speed like that, like vertically, something like that. So that's why the rotational speed for each stage is horizontal, vertical. Okay, always it doesn't change. The direction of doesn't change for axial compressor. The one that change only the relative and absolute velocity. Okay, because the blade only, the rotational speed blade only in this direction. Okay, So so this is inlet, okay. So this is our alpha. Alpha is the angle between the axis, okay, and C1, and this is beta, relative. Okay. Okay, beta. Okay, so this that is at the inlet, and at the outlet. Okay, I think I draw. Saya lukis yang. Okay, this one. Okay, imagine if we have blade. This picture, this figure. So we have. Okay, so each stage of compressor consists of a stator and rotor. Okay, a rotor and stator. Compressor, we start with rotor first. For turbine, is the opposite. We start with stator first. Stator, rotor. But for compressor, we start with rotor first. Rotor, stator, rotor, stator, rotor, stator. Depends on how many stage we have. So in this exercise, only one stage. We consider only one stage. Okay. So this is the first rotor 1. Okay. Rotor 1. Sekejap Wait. Okay, sorry. Okay, so we have okay, this is the blade inside the rotor. Okay, so the direction of U is this way. U. Okay, so and then from this, okay, exit. This is the W2. Okay, exit of the. Okay, so U remain the same, this direction. So to complete the triangle, we have C2. Okay. So again, this will be alpha 2, this will be beta 2. Okay. Okay, so and then we have stator. Okay, after rotor, we have stator for compressor. So the stator blade will be this way. Okay, so I only draw 2, but it has a lot, several. Okay, like this stator. So this is stator 1. Okay, so stator. And then okay, so and then repeat again. Exit is stator. So you have like this, okay. So C3, W3, and U. U is the same. So that's why in SA compressor, we don't really characterize it U1, U2, U3, etc. because U is the same. So U is the same for all the stage. Okay. So okay, so that's okay. So this is example of one stage, a single stage of a compressor. Let's say compressor. So you have rotor and stator. Okay. So remember, I explained in the lecture. Rotor is the one who is rotating. Okay. Rotor is the one. The blade of the rotor is the one which is rotate. Okay. So this energy from the rotor, this kinetic energy, because it's moving, so it's kinetic energy. This kinetic energy will be transferred to the fluid. Okay, So that's why in the stator, or this one is named diffuser, diffuser stator is the same. So in the stator, the fluid keep moving, the fluid can keep moving because it receives the kinetic energy from the rotor just now, from the rotor part. Okay? Okay? At this part, velocity increase, okay, receive kinetic energy from the blade, rotor blade. So the fluid, the air receive energy, kinetic energy. So in this part, the kinetic, in the stator, the kinetic energy will be changed because of the conservation of energy principle. The kinetic energy will be changed, converted to pressure energy. So that's why pressure rise, okay? And the velocity, kinetic energy decrease back. And we repeat the cycle. Okay. So back to the questions. Okay, so air at 1 bar and 15 degrees Celsius, which is around 288 just now, 288 Kelvin, enters a single stage essay compressor with a velocity of 420 meter per second. So inlet velocity, C1 is 120. Okay, there are no IGV. IGV is inlet guide vane. Okay, so I put a figure. Okay, this is IGV. So the function of IGV is actually okay, here to regulate the airflow and pressure because we want to minimize the work. At the first stage of compression, IGV has multiple triangular shaped vanes, so it's in triangular inside here, that allow the air to flow into the compressor in a swirl direction. Okay, so if we have IGV, the absolute velocity entering the essay compressor, it has a bit of an angle that we characterize as alpha. But here, if there are no IGV, means that we understand that the absolute velocity enters the fluid, the fluid enter the compressor at totally axial. So alpha is 0. There is no pre-swirl. Okay, the pre-swirl air reduce the amount of work needed from the main driver to spin the air entering the impeller. Okay, so if the IGV, the function of IGV is to swirl, okay, because it has a triangular shape, to swirl the airflow at the inlet of the compressor so that we can reduce the amount of work. Okay, but here there is no IGV, okay? And constant axial velocity is assumed throughout, okay? So here it assume CA, I think, okay, CA is constant. Means that CA1 equals to CA2, CA3. Okay, C1, C2 is CA3. Because we don't have the tangent component. In each stage, the rotor turning angle is 25 degree. Okay, rotor turning angle is 25 degree beta. The annular flow passes are shaped in such a way that the mean blade radius is 20 centimeter everywhere. The rotor speed is 9,000 RPM. So we have to change from minute to second. The polytropic efficiency is constant at 0.9. The blade height at the inlet is 5 cm. Okay. Okay, so specific work and mass flow rate. Okay, specific work and mass flow rate. So we have the triangle here, the velocity triangle. So we start with okay, what specific work. So okay, so in order to calculate specific work, we need to use those angle, okay, and absolute velocity calculation of C. So we need to use the beta and C. Okay, how do we start? We start with beta. Okay, we calculate beta 1, beta 2 because we have the rotational speed. Okay, jom. Ada dulu. Okay. Velocity triangle of this exercise example. The velocity triangle is like this. Okay. So this is W1, W2, W2, W2. Okay, because at the enter, at the inlet, C1 is actually, this is C2. Okay, so we want to calculate, we have just now 25 degree beta. Okay, beta 1 is okay, tangent beta 1 u over CA1. Okay, u over CA1. So change this u in meter per second, and we have CA 120 meter per second. Okay, compress enters a single stage as a compressor with a velocity 120. Okay, so from this one, we have beta 1, 57.52 degree. Okay, so this is beta 1, and then we have beta 2, minus 25 degree. Wait, yeah. Okay, so beta 1, beta 1 minus 25 degree, 57 minus 25 is 32. Okay, where do you get 35 in each? Because mentioned here in each stage the rotor turning angle is 25 degree. So from beta 2 to beta 1 to beta 2 is the difference is 25 degree. So we get 32.5 degree beta 2. Okay, then CU2, okay, then we use this value of beta 2 to get this one, tangent beta 2. Okay, I show you the equation. Show this step. This one, this one in this slide. You see one, tangent kurang lah. Okay, saya add yang ni. Exactly like this one, but okay, we can get the equation for tangent from the velocity triangle that we have sketched. Okay, so we have tangent beta u minus c, so beta here, beta 2, okay, beta 2, u minus c, u2 minus over CA2. Okay, I try to draw properly je lah. Kita tak nampak. Okay, saya redraw balik. I redraw back. Okay, try to see clearly. Okay, this is the triangle. Okay, This is the second triangle and the first triangle like this. Okay, because the triangle of the inlet are 90 degree here. Okay, because the fluid enter axially, total axial. So this C1 is straight vertically. Okay, and this is U, this section, and W1 velocity. Okay, this is the first triangle. The triangle at the inlet of the rotor. Okay, so U in this direction. So we have C1 axially and W1 relative velocity. Okay, so for this one, C1 is equal to CA1. Okay, and CU, okay, this direction. Okay. C1, C2, this is C2, and this is W2. Okay, U is the same. So for axial velocity, U is the same direction. C2 is this direction, so and then this one is W2. Okay. So this is alpha, okay, between the absolute velocity and the vertical line, and this is beta 2. Okay, for the inlet velocity, alpha 1 is 0, alpha 1 0. So this is the beta 1. Okay. So alpha 1 0 and also CU1 also 0, because there is no tangent component of the absolute velocity. Okay, but for 2, okay, at the outlet of the rotor, 2, we have the components CA1, CA2 and CU2, tangent and axial. Okay, so the axial CO2, CA2 is the same as CA1, but the CU2 will be this one, CU2. This direction, tangent direction, okay? There is no CU1, but there is CU2. CU2 exists. Okay, so what we were doing just now, to calculate beta, we know beta 2, but we want to use this equation to calculate CU, because this CU will be used to evaluate the specific work. Okay, so we use this one because we know the angle from beta 1 and then beta 2. We know those angles, so we use the knowledge of the angle to calculate the tangent component of absolute velocity, because the tangent component of the absolute velocity will be needed to calculate the specific work. Okay, tangent beta, okay, so here just now beta 2, you already get beta 2 32 degree, 32.5. Okay, so U we know from the RPS, rotational speed, U, and CA is constant, so CA1 equals to CA2 equals to 120 meter per second. So we can calculate CU, the tangent component of C2, absolute velocity. So from there we get CU2. From here, CU2 is 111 or 112, 11.9, 112 meter per second. Okay, so from this triangle, we look back, okay, tangent beta 2 is U, the total, okay, U minus CU2, because CU2 is only this part, so that's why U minus CU2, so we get this part, okay, over CA2. Okay, CA2 is equal to CA1, axial direction. Okay, so that's why U minus C. So even though all the function tangent in the lecture slides given, you don't need to memorize, or you can you can sketch back the velocity triangle, and then we can just rewrite the equation tangent. Okay, u minus cu2. Okay. So we have cu2 101 or 102 meter per second. Thus, the specific work, okay, specific work, whether you use Cu or you can also use tangent. Okay. So the specific work of the compressor, there are two equations. Okay, there are several actually. Two. Okay, I use two to calculate specific work. Ws specific work times the change in the tangent component of absolute velocity, which is actually cu2 minus cu1, but here cu1 is 0, so you only need cu2. Okay, this equation comes from actually in reference book that they show how do we derive this specific work. It's actually come from the definition from enthalpy, temperature, etc. And we have this equation. Okay, UCU2. So if we use this one, you get 21.11 kilogram, kilojoule per kilogram. Okay, or you can also, instead of using Cu, we can also use just use Ca and use those definition of angles that we know. Okay. This one is use median, tak suka sangat. Okay, U1, CU, CA1. Lah, okay. It's okay, I use this one. Okay, so you can also use CA, tangent beta 1 minus tangent beta 2, because we have tangent, etc. So the answer will be the same, 21 around the same, kilojoule per kilogram. Okay. Okay, so this is the equation, okay, for W specific work. Okay, I'm not sure the derivation because it's too long. The derivation, how do we arrive from the enthalpy, etc., to get the specific work equation? Because we use enthalpy and then the velocity triangle. Okay, ada derivation dia lah tapi panjang sangat. Okay, next, the mass flow rate. So to calculate the mass flow rate is kind of the same as previously. Okay, the equation is the same, rho 1 CA1A. So the process also the same. You calculate. Okay, we know CA1. We already know CA. So just like just now, so we calculate T1 temperature and the P pressure, density, and then we arrive at the mass flow rate. So that one is the same as previously. So CA1 is known. Okay, the step is the same. So we calculate T1. So T1, T total 1 minus T total 1 minus C1 squared 2 CP. So you get 280.84 Kelvin. And then P1. Okay, P1 using the P total, etc. P total equation. So we get P1 0.916 bar. We use bar. Okay, because the total the total pressure is 1 bar. And then density, the ideal gas equation, P over RT. So we get 1.136. So again, around 1 kilogram per meter cube. And lastly, we arrive at M. Okay, M. The one that is different is the area. Okay, so this time for axial compressor, the area is not pi over 4d squared anymore. Okay, because we have to understand how the fluid enter the stage axially. Okay, so the area for axial compressor will be in terms of 2 pi r radius h. H is the blade height. Okay, that's why the blade height is given here, 5 cm. And R is the mean blade radius, 20 centimeter. Okay, why? If you understand how the fluid flow axially, okay, gambar tak nampak sangat. Okay, so 2 pi R is the lilitan, circumference. Okay, so we imagine because the fluid will enter axially and will rotate this way, right? So we only take the circumference, okay, the outside, okay, the outer is like the outer area pi. Okay, so that's why we use this 2 pi r, 2 pi r times the blade height, okay. The blade height dia tunjuk kat sini tak nampak. Do we have this? Boleh lah. Okay. Tak, gambar tak ada sangat. Okay, so the blade height is this one. Okay, so the fluid enters axially. So we imagine it rotates like that. So we only consider the outer part, okay, which is the circumference 2 pi r, okay, times the height, okay, the total height. Okay, sorry, the height is this one, okay, throughout the total of the stage height. Okay, 2 pi r minus the multiply with the height. Okay, so that's why we have the area here. Takut korang tak faham. Okay, so let's cuba lukis, takut tak faham sangat. Okay, so this is axial. If we have several axial several stage. Okay, so this is the mean radius. Tengah-tengah ni. Okay, at the middle, this is the mean radius. Okay, so it rotates. Okay, U this way, rotational this way, so it rotates. So we only consider the circumference, lilitan luar tu, 2 pi r. Okay, so 2 pi r, imagine for one blade, okay, like that. And we times it with h. Okay, the total length, height of the axial. So 2 pi r is only one, and then we multiply for the whole stage height, h. Okay, so that is the mass flow rate for axial compressor. Okay, so rho 1 CA1 2 pi RH. So what do we get? We get equals to 8.57 kilogram per second. Okay, so this is the mass flow rate. Okay ke? Okay everyone?
Okay, Doktor.
Okay, over 10. Can we do just another one? Axial flow turbine. Okay. This is axial flow turbine. So if you understand the axial compressor, so it's just the opposite. Just like I mentioned just now, we start with, for turbine, we start with stator. Stator, rotor. Okay, depends on how many stage we have. Okay. Angles, pressure. Okay, where is that? Okay. Okay. Start as a turbine. Pressure ratio of the stage. Okay, to get the pressure ratio, so for turbine, it's the opposite of the compressor. So pressure ratio will be the total pressure at the outlet 3/1. Okay, so okay, so in order to use this, we need total temperature first. Okay, TO3. Okay, wait, we read first. A single stage axial flow gas turbine has the following data. Turbine inlet temperature 1100 Kelvin. So that is T total 101 1100 Kelvin. Okay. This T total 101,000 is the same for 2. Okay. Just like the compressor just now, 1 is the inlet of the for turbine inlet of the stator. 2 is the location outlet of the stator, and 3 is the point outlet of the rotor. For turbine, we have stator 1, rotor 1, right? So this is point 1, this is point 2, and this is point 3. 1, 2, 3. Okay, like this. Okay. So turbine temperature 1100 is at this point. Okay. So the since 1 and 2 is the inlet and outlet of the stator, so and stator actually doesn't move, rotor is the one who is moving. So the temperature of the total temperature T1 and T2 is the same. So T total 1100 is the same as T total 2. Okay. What else? Okay, turbine inlet total pressure 3.4 bar. Stage temperature drop 1404 Kelvin. So the total temperature drop after exiting rotor. Isentropic efficiency 0.9. Mean blade speed U. Okay, so U is constant throughout the stage 298. Mass flow rate M 18.75. Flow coefficient 0.95. Convergent nozzle is choke, okay, because we need to use this definition later on. The nozzle is assumed to be adiabatic as if velocity is constant. Okay. Apa ya? Okay, T total 3. Okay. So to calculate T total 3 first, we can use the value 1100 Kelvin. Okay, given. Because this one T total Y equals to T total 2. Okay, and the total pressure drop. Okay, total pressure drop is 144. This is the total pressure drop. So the pressure drop from here to here is, okay, the total pressure, the change in total pressure is 144 Kelvin. And we know that this one is the same value, so only the change will occur in this part 2 to 3. So to calculate T total 3, T total 1 minus the change, so we have 956 Kelvin. Okay. And then, okay. P total, include in pressure, because we have T total 3 over T01. This is gamma minus 1. Okay, this part, gamma, okay, so gamma, PO1 just now, so we have 0.533, the ratio, 0.533, pressure ratio. So because the turbine is it's like the opposite of the compressor, so we have to change it, inverse PO1 over PO3. Okay. So inverse is 1.875. Okay. So that is the pressure ratio of the one stage of the turbine. It's a turbine. Okay, 1.875. Huh? So we just use the ideal gas equation. Okay, next. Okay, flow angles. Ini panjang sikit. Okay, tak apa. Okay, since the nozzle is choked, okay, the nozzle is choked. Okay, nozzle is like it's like at the beginning of the turbine. The function is like the stator. So sometimes because we can also call the function is like the stator. Okay, so nozzle is choked. So we have C2 gamma R square root gamma RT2. Okay, because choke means Mach number is equals to 1. Okay, so the absolute velocity is equal to the speed of sound, square root gamma RT2. And we know this equation, okay, for choke nozzle, right? Okay, this one, because Mach number equals to 1, so we have this equation, remember in the previous chapter. So, so this one gamma plus 1 over 2, we get 1.165. So we have T2 okay, so we get T2 944.2 Kelvin. Okay, T2 is like the T7 exit nozzle, something like that, like the previous chapter. Okay, so T2 is 944.2 Kelvin. And back to this one, C2, 600 meter per second. Okay, you substitute T2 inside the square root. Okay, and then to calculate each angle, what do we have? Angle alpha, alpha 3, etc. So we can calculate alpha first, alpha 2 first. Okay. So alpha 2 cosinus alpha 2. Tadi kita tak lukis diagram. Cosinus alpha 2. Okay. I draw the velocity triangle first. Velocity triangle. We have like this, something like this. This is U. Okay, so U is the same. This is C2, the absolute velocity. Okay, for turbine, we only focus on the location 2 and 3 because that is the rotor part. Okay, that is moving. 2, C2, so this is W3. W2, sorry, W2. Okay, so next part, the triangle. Something like this. So this is W3 and this is C3. Okay. So this part is the axial component of the absolute velocity. Okay, so alpha 2. Alpha 2 is the angle between, okay, this is alpha 2, angle between the absolute velocity and the axis, axial axis. And beta 2 is this one. Okay, beta 2. Between the axis and the relative velocity. So we calculate alpha 2 first. So alpha 2, how do we calculate alpha 2? We use cosinus because we know C2. Okay, we have calculated C2 just now because we know C2. Okay, look at this triangle. Imagine, okay, this is imagine 90 degree here. Okay, only this triangle, okay, this triangle. So cosinus, we use cosinus because this is CA2. Okay, CA is constant. So we know CA and we know C2. Okay, C2 we have calculated just now using the Mach number just now. Okay, using the choke convergent nozzle just now. Okay, so we know C2 and we know CA2. So we use cosinus alpha. Cosinus alpha. So cosinus CA2 over C2. Okay. So CA2 is the axial velocity, axial component. Okay. Axial component we have to calculate first. Okay. C2 is the 600 just now. 600 meter per second. Okay. CA2, we use the knowledge of flow coefficient. Okay, the definition of flow coefficient. Flow coefficient we write it as phi. Okay, flow coefficient. Flow coefficient is CA2 sini. Okay. CA over U. Okay. This is the definition of flow coefficient, CA over U. So CA is constant. So we have CA2 is 5 times U. Flow coefficient is 0.95 times the rotational speed, 298. Okay. So we have alpha 2, 62 degree. Okay, from cosinus. We use the flow coefficient knowledge. Flow coefficient times U, the rotational speed, over 600, the C2 that we have calculated just now. So we get 62 degree for alpha 2. Okay? So we need to use the knowledge of flow coefficient. Okay? Next, we proceed with beta. Okay, beta is here. Okay, so beta. Okay, we use this one. Okay, we can use this one. Beta. This is AC compressor, sorry. AC, wait AC turbine. Saya dah bagi tak? Kita bagi. Tak bagi. Okay, tak apa, it's okay. Okay, so for AC turbine, the relation between beta and alpha, you can use this one. Okay. U over CA equals to tangent alpha 2 minus tangent beta 2. Okay, U over CA is tangent alpha 2 minus tangent beta 2. Actually, you can derive by yourself this equation. Try to write tangent alpha 2 equation first, and then try to write tangent beta 2 at one part, and then you combine both of them, and then you get tangent alpha 2 minus tangent beta 2 is U over CA. Okay? I show one example. Okay, so tangent alpha 2, the definition, tangent alpha 2 is okay, U over C2, right? U over C2. Okay? Tangent alpha 2. Tangent beta 2. Tangent beta 2, this one is CU2. CU2 over C2 tangent. This is this one. Tangent alpha 2. Okay, tangent alpha 2 is U plus CU2 over CA2. Tangent beta 2 is CU2 kat sini CU2. CU2 is the whole. Okay, tangent alpha 2 again, CU2 over CA2. Okay, tangent beta 2 is CU2 minus U. CU2 minus U over CA2. Okay, so if you combine tangent alpha 2 with tangent beta 2, the CU is eliminated. Okay? Tangent alpha 2 minus tangent beta 2, then this CU is eliminated. So you only have U over CA2. CA is constant, so CA2 is equal to CA. So that's why I said just now, you don't need to, even though you don't know, okay, about this relation, you can derive by your own self. Tangent alpha, tangent beta, etc. Okay? So we use this one, U over CA, because we know alpha 2, okay, we want to calculate beta 2, so we get beta 2 39.6 or around 40 degree. Okay. Beta 2 39.6 degree. Okay, from this relation. Okay. Next, alpha 3 and then beta 3, okay? And then we finish with beta 3. Okay, so to calculate alpha 3, we use the specific work that we have calculated in first question. Okay, so alpha 3, this one 39.6, huh? Okay, alpha 3. So WS, the specific work just now, UCA, specific work just now, UCA. Okay, another relation for this, tangent alpha 2 plus tangent alpha 3. UCA tangent alpha 2 plus tangent alpha 3. Now again, there are several equations for specific work. So this one we use alpha 2 and alpha 3 because we want to calculate alpha 3. Okay, so tangent alpha 3 we have specific work specific work okay, sorry. Tangent alpha 3. So the specific work is also can be written as Cp delta T0. Okay, this definition from thermodynamics. So we have Cp delta T0. Okay. Alpha 3 is Cp delta T0 over UCA minus tangent alpha 2. Tangent, okay, from here, tangent alpha 3 is equals to WS is Cp delta T0 over UCA minus tangent alpha 2. So we get alpha 3. Okay, so alpha 3 is about 4.5 degree. 4.5 degree. Okay, last is beta 3. The same, you use the UCA. So UCA, this time that links alpha 3 and beta 3. UCA tangent beta 3 minus tangent alpha 3. Okay, another relation between U over CA. Again, this one you can try to derive from the velocity triangle. So we have beta 3, 48.5 degree. Okay. So basically, the most important part is that we have to first to try to sketch. Okay, so this is in the lecture slide. This is the axial flow turbine velocity triangle. Okay, so once we get the problem, we try to sketch the velocity triangle so that we understand where the position of the velocity C, U, W, and the angles alpha, beta. So from there, we can use the tangent, cosinus, etc. to calculate all those angles. Okay, so for this one in the lecture slides, okay, here if we have alpha 1 in our exercise, it's not alpha 1 is 0, so that's why we don't have this angle. Okay, the C1 is equal to CA directly, and then it enters the nozzle blades. Okay, it's like nozzle is like the stator blade. Okay, and then it exits. Okay, U actually, okay, in this direction. So the direction of the blade, okay, this is the absolute velocity, follows the direction of the blades, the nozzle blade just now. Okay, So absolute plus combined with the rotational speed, so we get the relative velocity V or W here. Okay, so beta is the angle between the relative velocity and the this axis line. Okay, and then the fluid will enter rotor. Okay, after nozzle or stator, it will enter rotor. So it enter rotor this way and it exit the rotor this way. Okay, so from after the exit of the rotor, we know the relative velocity. Okay, remember why the relative velocity? Wait, I'll explain. Okay, remember, it's the rotor. Rotor is the one who is rotating, okay, who does work and convert kinetic energy, etc. Okay, so when exiting the rotor blades, okay, the fluid will have a certain velocity, which is characterized by, this is called relative velocity, because the velocity of the fluid exiting the rotor depends on the rotational speed. Okay, so actually the absolute velocity of the fluid is c, but what we measure when the fluid exiting the rotor is relative velocity. So that's why this relative velocity follows the rotor blade's direction. Okay. So I repeat again, how do we sketch the velocity diagram triangles? Okay, first this one, we know this one. So is at the enter of the nozzle inlet. Okay, so in this direction, so is if the fluid enter totally axially, so alpha 1 is 0, so C1 is equal to CA1 in this direction, horizontal or straight like that. Okay, so we have nozzle. So nozzle blade is this way, kind of like this. So when exiting the nozzle blades, okay, the rotational speed stay the same for axial turbine or axial compressor. U is the same. So we know it is in this direction, U. Okay. And absolute velocity, how do we get the direction of the absolute velocity is from the direction of the blades here. Okay, the direction of the blades here. So we imagine the fluid is in this direction. So the fluid exiting the nozzle blades is C2, the absolute velocity, because the nozzle or the stator practically doesn't move. It's the fluid who is moving, who is rotating. So the fluid, the air exiting the nozzle, the velocity of the fluid is the absolute velocity, the real velocity of the fluid. Okay, the exact or the real velocity of the fluid, the absolute velocity. Okay, because the nozzle doesn't move. Okay, so when we know the direction of C plus the rotational direction, so to complete the triangle, we can complete with the relative velocity direction. Okay, next for rotor, we know here rotor is moving. So when rotor is moving, the velocity of the fluid exiting the rotor is actually the relative velocity, because we have the rotating rotor plus the fluid. Okay, the velocity of the fluid. So we follow the velocity, the direction of the velocity exiting the rotor, which is the relative velocity, because we have the absolute plus the rotational speed of the blade. Okay, so we follow this direction, V3 or W3. That is relative velocity. Okay. Just now in this whiteboard, just now I draw it the U in this way, and I paste it the both of this triangle in the same figure. Okay, the same diagram. So that's why this collapse with this one just now. But if you separate it, so it is this way. This now, okay. So just now we calculate alpha 2. Alpha 2 is this one. Okay, alpha 2, beta 2, and this one alpha 3 and beta 3. Okay. Okay. So I hope you clear with the direction just now. What else if I want to sum up? This one is for compressor. As a compressor also, okay, entering the rotor and exiting the rotor. So this is the direction of the velocity triangle. Okay, so we have alpha, the U. Okay, so the direction of the U is the same. It's just the absolute and relative velocity who are modified. Okay, throughout the stage. Okay. Apa lagi? I think that's all. This one. This is the centrifugal compressor, not axial. Okay, so remember just now what else that we have to remember other than velocity triangle is how do we calculate the mass flow rate. Okay, so we calculate the mass flow rate, especially the area part, depends on how the fluid flow. Okay, that's why you have to understand how the fluid flow entering the compressor or the turbine. So for centrifugal, the fluid will enter this way and comes out this way. This is the side view or the front view. The fluid will enter at the center here and comes out. Depends on the radius, radially, in the radial plane. Okay, so the fluid entering at the middle, in the center, okay, this way. So that's why just now when we calculate the area, to calculate the mass flow rate, the area, you have to take into consideration the whole area of this, the whole diameter of this I-tip diameter minus the root diameter. Okay? Oh, jatuh. Okay, so like this. It enter at the center and it comes out radially, depends on the radius. Okay? Radially. Okay? And for axial, mass flow rate, okay, we consider each stage, okay, we consider that the fluid enters flow at the outer part, okay, macam lilitan circumference. So we use the circumference equation 2 pi r, okay, times the height, the total height of the stage. Okay, because 2 pi r is only for one rotation that, okay, and then we have to multiply for all the stage, the length of the stage. So that is the blade height h. Okay, so that is for mass flow rate for axial compressor. Okay, so I think that's all. Actually, there is another there's another exercise left, but it's okay. We try to do it. We are going to see each other in at least one more class online live. So we try to do this in the future class. Okay, because I think 3 exercise today is already full for you guys to digest. So I let you guys understand first. Okay, so this one we will do in the future, inshallah, 2-3 weeks to come. Okay. So I finish there. So attendance, wait. Okay, wait. Okay, stop sharing first. Okay. Stop recording.